All right, so now we are at the end of Chapter 9, looking at Section 9.5, where we're no longer focused on just dealing with trigonometric identities, but instead we are solving trigonometric equations. And a lot of the work that we've done up until this point in Chapter 9 will actually help with this process of solving equations. So before we do that, let's review just briefly what it means to solve an equation. You spend a whole lot of time doing this in algebra. So, for example, if I gave you an equation like this one, 3x minus 1 equals 5. To solve this equation is to find a value that we could plug in for this x that would make this true. So in particular, I'm looking for something that I could plug in for x such that this side becomes 5, giving me 5 equals 5, something that's true. Obviously, guess and check is one way to do that, but in algebra, you learn much better methods than that. I could solve this equation by adding 1 to both sides, giving me 3x equals 6, and then dividing both sides by 3, giving me x equals 2. And so this equation has one solution, x equals 2. But as you progress through algebra, you deal with more and more complicated equations. A lot of time is spent on polynomial equations, things like this one down here. And you learn that equations of these types tend to have more than just one solution. So, for example, x cubed minus x squared minus 3x equals 0. This is an equation that you could solve by factoring. And if you did that and use the zero product property that you learn in algebra, you'd find that there are 3 solutions to this equation, 0, 6, and negative 5. You can verify each one of these if you want just by plugging them in. A trigonometric equation is a similar idea, but instead of dealing with linear expressions like this one or polynomial expressions, linear are a type of polynomial, we're dealing with equations that involve a trigonometric function somewhere, or several trigonometric functions oftentimes. An example of a very simple trigonometric equation is the one that we see right here. Sine of x equals 1/2. We're looking for all possible values of x that I could plug into this to make this true. Now, this is not an identity. Remember, the difference between just any old equation and an identity is that an identity will be true no matter what I plug in for x. But that's clearly not the case here. If I plug in a 0 for x, for example, sine of 0 is equal to 0, not 1/2. So this has solutions, but it's not just every number in existence that would work for x here. Trigonometric equations can get very, very complicated. For example, this one, sine of 2x over cotangent of x minus 3 tangent of x equals cosine squared of 3x. Solving an equation like this would be a very difficult process. It would involve a lot of steps. Probably a lot of identities would go into simplifying things down to make this solvable. So sometimes when we're solving equations, one approach that you can take is to graph either side, or sorry, I should say both sides of the equation. So each side of this is a function, sine of 2x over cotangent of x minus 3 tangent of x. If I graphed that function, y equals that thing, then what I would end up with is the red graph that you're seeing here. So you see something that looks kind of similar to a secant or a cosecant graph, but not exactly the same, because these U shapes are more narrow than these upside down U shapes, but they're kind of similar. Cosine squared of 3x is the blue graph. And this is not something I would ever ask you to graph by hand. I should point that out. Even though we did a lot of graphing in Chapter 8, we never graphed anything that resembled this. So this is something that you would use a graphing utility for, either a graphing calculator or a website like Desmos. That's where I got my graph from. And then what are you doing if you're looking for solutions? Well, these are two different graphs, but you notice they intersect at different points. And something you learn in algebra is that those points of intersection give us solutions to equations like this one. In particular, the x-coordinate of any point of intersection between these two graphs would represent a solution to this equation. Now, if you go through and count them, 1, 2, 3, 4, 5, 6, 7, 8. I see 8 solutions in this graph right here. But this would definitely have more than 8 solutions because I'm only looking at part of the graph. If I were to zoom out, you would see that this graph continues this pattern. And that's not surprising. Trigonometric functions are periodic, which means they have a repeating pattern. So what we're seeing here is just a piece of a pattern that goes infinitely in both directions. That means I'm going to keep getting points of intersection the further and further I move towards the right or towards the left. And that implies that there would be an infinite number of points of intersection, which corresponds to an infinite number of solutions to an equation of this type. And that's generally the case. For the most part, trigonometric equations tend to have infinitely many solutions because of their periodic nature. So that's going to have to play into how we write our solution sets, because obviously you can't just write out an infinite number of numbers. You just don't have time for that. So you'll see in a little bit how we handle writing an infinite number of solutions. But before we get to that, there's really two cases that we tend to look at when solving trigonometric equations. There is getting the entire solution set, which we just said is an infinite number of solutions most of the time. Or sometimes, because trigonometric equations are, again, periodic, sometimes we only care about the solutions on a particular interval. Oftentimes, you'll see problems that say, solve this equation on the interval 0 to 2 pi. In other words, what are all of the solutions to an equation of this type where the angle x lives within one revolution of that unit circle? So we're going to look at both types of solving trigonometric equations, on an interval and on what we call a what we call a general solution. I have like a blank page printed out there for some reason. Okay, so let's return to that first example of an equation, a trigonometric equation that we looked at. Sine of x equals 1/2. Let's approach this first by trying to solve that equation, sine of x equals 1/2, on the interval 0 to 2 pi. Now, one thing I want to point out about this interval is that it's a half-open interval. There's a square bracket here, and there's an open parenthesis here. What this means is that this interval contains the number 0, but it does not contain the number 2 pi, and it contains everything between them as well. The reason for that is because the angle 0 is coterminal to the angle 2 pi, and so in a certain sense, 2 pi is kind of redundant if we've already considered 0. But basically, if I'm trying to solve an equation of this type, what I'm trying to do is find all values of x such that sine of x equals 1/2. And 1/2 is a familiar number when you think about the unit circle. By this point, you should have your entire unit circle memorized. And you should know that there are two places where sine of x is equal to 1/2. One of those is when x is equal to pi over 6. The other is when x is equal to 5 pi over 6. A couple of things I want to point out about this. One, notice I'm using radian measure. And as we have been saying kind of from the beginning of the course, 95% of the time, 99% of the time, you're going to want to give answers in radians, not degrees. And again, that's because in calculus, radians are far, far superior to degrees as far as how we measure angles. And the reason why will become apparent in calculus 1. So that's the first thing, is that these are measured in radians, not degrees, unless specified otherwise. But secondly, I want to point something out that might have occurred to some of you as we're talking this through. Normally, when you're solving an equation in algebra, you're thinking about doing inverse operations. So inverse operations are basically trying to undo what's been done on one side of an equation. What I mean by that is this. Here by first equation I showed you, 3x minus 1 equals 5. The steps that we talked through for solving this and use what are called inverse operations. If I'm subtracting a 1 on this side, to undo that, I would add a 1 to both sides. So addition is the inverse of subtraction. Then I would divide by 3 because right now the x is being multiplied by 3, using division to undo multiplication. That's the way you're trained to think about solving equations from elementary algebra. Now, is there an inverse operation that could be used here? And the answer is yes, technically yes. We talked about that in section 8.3 where we introduced the inverse trigonometric functions. You could take an inverse sine of both sides, but that presents a very, very critical problem. If I took the inverse sine of both sides of this equation, then that would say that x is equal to the inverse sine of 1/2. But what is the inverse sine of 1/2? Well, remember, when you take an inverse sine of a number, you're supposed to be looking for values between negative pi over 2 and positive pi over 2. Inverse sine of 1/2 is pi over 6. So taking the inverse sine of both sides would give me this solution, but it would never give me this one. So it's not enough generally to take just an inverse trig function to solve an equation, because that will only ever give you one solution when, like we said, these equations tend to have infinitely many solutions. And even if we're just solving on an interval, most of the time you're going to get at least 2 solutions. So you need to avoid using inverse trigonometric functions, except for a couple of cases that we will look at as we go through some examples in a bit. It's far better to use your knowledge of the unit circle, like we did, to try and solve this. All right, so that was an example of solving a very, very simple trigonometric equation on an interval. But what if we're looking for the general solution, meaning all of those infinitely many solutions that we would expect to come from a trigonometric equation? Well, in that case, we're no longer just sticking to one revolution around the unit circle, which is what this interval represents. We need to consider all angles, whether positive or negative, and whether or not they involve several revolutions clockwise or counterclockwise around the unit circle. The way that we're going to do that is to take our answer that we already got for solving sine of x equals 1/2 on the interval 0 to 2 pi. And then we're going to think of all the angles that are coterminal to those answers. Because any angle that's coterminal to pi over 6, the sine of that angle will still equal 1/2, based on what we learned in chapter 7 about these trigonometric functions. Similarly, any answer or any angle that's coterminal to 5 pi over 6 will also be a solution to this for the same reasoning, the same logic. So really what finding a general solution boils down to is first looking at all the solutions within one revolution of the unit circle, and then determining all of the angles coterminal to those solutions. So because we've already gone through the work here, pi over 6 and 5 pi over 6 are obviously solutions to this equation. How do you determine something that's coterminal to each of these? Well, remember, two angles are coterminal if they differ by a multiple of 2 pi. So really, I just need to consider all possible multiples of 2 pi plus pi over 6, and all possible multiples of 2 pi plus 5 pi over 6. We can represent that this way. Notice it says x equals pi over 6, the first solution, plus 2 pi k. Or x equals 5 pi over 6, the other solution, plus 2 pi k. And then this symbol, you may not have seen these symbols before. This is using a set notation. So this little symbol right here means is an element of, and this kind of thickened capital Z stands for the set of integers. So what this is saying is that k is an integer, or k is, we're considering the solutions of these forms, you know, pi over 6 plus 2 pi k, or 5 pi over 6 plus 2 pi k, for all possible integers k that can be plugged into either one of these. That would account for all possible multiples of 2 pi. Now, even though I'm using this notation here, in general, I'm not going to write this, because if I simply write my solution set this way, x equals pi over 6 plus 2 pi k, x equals 5 pi over 6 plus 2 pi k, we're going to assume that it's implied that k represents any of the integers. You know, I can plug in any integer for k here, and that gives me another solution to this equation. Okay, so this symbol, I'm showing it to you once, but in general, we're going to leave this off and just understand that this is implied when we write a solution set this way. So let's look at another example. We're actually going to go through a ton of examples in this section because there's a lot of variety that you can encounter when we're dealing with trigonometric equations. Starting with this guy. I want to solve -2 cosine of x equals root 2. Now, in an example like this where I only have one trigonometric function and it's not raised to any powers or anything, this is very similar to how you solve a linear equation in algebra. but we're going to think of cosine of x initially as like our variable. So I'm going to try and isolate that cosine of x there. I can do that by dividing both sides by -2 first, giving me cosine of x equals -√2 over 2. Okay? Now, again, remember, you can take an inverse cosine of both sides of this to solve for x, but that's only going to give you one solution. And as we've already seen, there's probably more than one solution to find. So that's not a good approach. Instead, notice that -√2 over 2 is a familiar value that we see from our unit circle. Where on the unit circle is cosine of x equal to -√2 over 2? Well, cosine is negative in the second and third quadrants, and my solution set here is going to be, just again from my knowledge of the unit circle, 3 pi over 4, that's the solution in the second quadrant, and 5 pi over 4. That just comes straight from my knowledge of the unit circle. So it looks like I showed almost no work here, but that's because there really wasn't much in the way of work to show. Really just this first step, dividing both sides by -2. A couple of things I want to point out. I did not add 2 pi k to either of these, and the reason for that is because it said to solve this equation on this interval. So we're not considering all possible solutions. We're not looking at solutions that are coterminal to these. We're only looking throughout that one revolution of the unit circle. The second thing I want to point out is I didn't write x equals 3 pi over 4 and 5 pi, or x equals 5 pi over 4, although I could have written that. Something we learn in algebra is that when you're solving equations that have multiple solutions like this, it's more efficient to write it in set notation, which is what I have here. So this is my solution. That was a very straightforward one. They're going to gradually get more complicated as we go. Okay, here's another example. I want to solve tangent of x equals -√3, and again, we're looking on that interval 0 to 2 pi. Okay, this one is going to feel very much like the previous example. The tangent of x is the only trigonometric function showing up in this entire equation, and it's already isolated on the left-hand side. So really what this boils down to is knowing my unit circle again. Where in the unit circle is tangent of x equal to -√3? Well, tangent, I know, is negative in the second and fourth quadrants. So I'm looking throughout the second and fourth quadrants for a solution here. And I know, again, if you know your unit circle, I know that in the second and fourth quadrants, the solutions to this would be 2 pi over 3, that's the second quadrant, and then 5 pi over 3 in the fourth quadrant. Both of those would be solutions. So again, in an example like this, there doesn't appear to really be any work to show. That's not going to be the trend. There is going to be much more work that we need to show in the following examples, but this is just to kind of warm you up to the idea of how we think about solving these types of equations. Okay, so let's bring the difficulty level up a little bit. This time we want to solve 5 sine of x plus 1, that's in parentheses there, equals 4 plus 3 sine of x. And here, again, this is very, very similar to solving a linear equation in algebra. The sine of x that I see here and here, let's think of that like a variable. Think of it as just an x. What we'd be trying to do here is isolate the x, or isolate the variable. So I'm going to start by distributing the 5 on the left-hand side of that equation. 5 sine of x plus 5 equals 4 plus 3 sine of x. Okay, now what we would do in algebra, if you have variables on both sides of an equation, generally what you do is try to collect them all on one side and then move all of your constants over to the other side. That's the standard approach for solving linear equations. So I would subtract 3 sine of x from both sides. 5 sine of x minus 3 sine of x would be 2 sine of x. And then I would also subtract this 5 from both sides. So 4 minus 5, that's -1. Okay? Then the goal, again, is to isolate sine of x. So I can divide both sides by 2 to get rid of that. Now I have sine of x equals -1/2. Okay? Having done that, notice this looks really, really similar to the example we looked at when we were talking through solving trigonometric equations, except in that case the 1/2 was positive. So similar idea. Where is sine of x negative? In the third and fourth quadrants. And what values on the unit circle then in those quadrants would give me sine of x equals negative 1/2? Well, that would be at 7 pi over 6 and 11 pi over 6. Those are the two solutions for this equation. Although I just realized something. This is the first example that we looked at that didn't say it only wanted solutions in one revolution of the unit circle. It didn't say on the interval 0 to 2 pi. So even though this is correct, these are solutions, I shouldn't box that because I'm not done. I actually need to consider all angles coterminal to each one of these. So let me change how I write my answer. X is equal to 7 pi over 6 plus 2 pi k, as we saw before. X equals 11 pi over 6 plus 2 pi k. And again, I'm not going to bother with that notation that says k is an integer, because we're assuming when we see these k's, it's implicit that they are integers. Okay, so again, you have to be careful. I almost missed it on this one, but you have to look and make sure that it's not asking you to solve on just an interval. If it doesn't say anything about an interval, the assumption is that we're looking for all solutions or the general solution. Notice this example down here does the same thing. It doesn't say on the interval 0 to 2 pi. It's saying solve this equation. So we need a general solution again. How would we solve this one? Let's see if we could take a similar approach to what we just did in the previous couple of equations, which is to isolate my trigonometric function. I only see one showing up, cosine, but it's also being squared, so I'm going to have to take a square root at some point in this process. I'm going to start by adding the 5 to both sides so that I get 4 cosine squared of x equals 3. Negative 2 plus 5 would be 3. Then I'm going to divide both sides by 4. Cosine squared of x equals 3/4. And now, because I'm squaring the cosine of x on this side, I can undo that by taking a square root of both sides, giving me cosine of x equals. Now, first of all, what is the square root of 3/4? When you take the square root of a fraction, it's the same thing as taking the square root of its numerator and denominator separately. The square root of 3 I would just write as root 3. The square root of 4 is a perfect square. Its square root is 2, so I don't need to leave that under a radical. It can just be written this way. In addition to that, because I took square roots of both sides of an equation, we learn in algebra that we need to also include a plus or minus here. So now I'm not just thinking of where cosine of x is equal to root 3 over 2. I also have to look for where cosine of x is equal to negative root 3 over 2. We're including both the positive and negative values here. This is going to lead to 4 solutions in the unit circle, because in all 4 quadrants I can find an angle where cosine of x is either equal to positive root 3 over 2 or negative root 3 over 2. And again, based on my knowledge of the unit circle, that's going to occur at pi over 6. It's going to occur at 5 pi over 6, 7 pi over 6, and 11 pi over 6. And again, we're looking for general solutions this time. We're not interested in just this one revolution throughout the unit circle. So for each one of these, I have to include this plus 2 pi k now. Just like this. Okay? So that had a much more involved solution set, but that's generally what you're looking at when you deal with equations of this type. Let's keep on rolling. All right, now this seems like a relatively simple equation, but the noticeable thing here is that my angle looks different. It says solve sine of x minus pi over 4 equals 1. There's a couple of approaches you could take here. One approach is to use my difference formula or my difference identity for the sine function to expand this thing out and then try to solve what you end up with. And that's a totally valid approach. It's very doable, but it's actually easier to take a slightly different approach. let's look at the x minus pi over 4 here and kind of ignore the fact that it's a complicated looking angle. Let's just think of it for a second as if it were just x. Where is sine of x equal to 1? Well, I know from my knowledge of the unit circle that occurs in one place on the unit circle. It occurs at pi over 2. Okay, so I need the angle in here, the angle that I'm taking the sine of, to be equal to pi over 2. Now, it is saying that we need a general solution as well, so I would also need to add plus 2 pi k to get that general solution. But we don't want to say x equals this, because again, it's not x that we're taking the sine of. It's x minus pi over 4 that we're taking the sine of. So I'm actually going to take the entire angle on the inside, x minus pi over 4, and set that equal to the thing that I decided the sine of would be equal to 1. Now I can just solve this for x. And I would do that by adding pi over 4 to both sides. That's going to get rid of the minus pi over 4 here. If I add pi over 4 to both sides, because that's a constant and pi over 2 is another constant, I would just add these two fractions using a common denominator. Pi over 2 plus pi over 4 is 3 pi over 4. And so this ends up being my solution. Now, if you're ever concerned that you've done something wrong, and you're looking at a general solution like this, and you're trying to think, is this correct? Did I get the right solution here? What you could do is take this and plug in different values for k, different integers, and see if the result works in the original equation. In algebra, we emphasize this really heavily, checking your solutions by plugging them in. So for example, if I plug a 0 in for k, this term goes away, and I get 3 pi over 4. If I plug 3 pi over 4 in for my x here, the parentheses are telling me do the thing in parentheses first. 3 pi over 4 minus pi over 4 is equal to pi over 2. Sine of pi over 2 is 1, so that worked. What if I plug in a 1 for k? Well, that's just 3 pi over 4 plus 2 pi, which is an angle that's coterminal to 3 pi over 4. I would end up doing a subtraction here, and I would get pi over 2 plus 2 pi, which would still have a sine of 1. So this seems to check out if I start plugging some stuff in. Okay, I think this is a good place to stop this video. We'll keep going with the examples in the next one.